In this lecture, we shall discuss about the quantum theory of hydrogen-like atom. Um, this is the nucleus, and let us suppose that we have Z number of protons in the nucleus, and around this nucleus an electron is revolving. And let us suppose that the distance between the electron and the nucleus is small r, and the potential energy of the electron with respect to this nucleus is this minus z e squared divided by 4 pi epsilon naught r. Okay, this potential energy of the electron is spherically symmetric, and it is dependent only on the radial distance. It does not depend on the angular variables theta and phi. The hydrogen-like atom is a two-particle system consisting of an electron with charge -e and an atomic nucleus with charge +Ze, where Z is the atomic number or the number of protons in the nucleus. Since the electron is very much faster than the nuclear particles, it is assumed that the nucleus is stationary as compared to the electron. The Schrödinger equation for the hydrogen-like atom will then be the equation for a single electron moving around the nucleus. Thus, the Schrödinger equation for the hydrogen atom can be written as we have twice me and then del square operator plus the potential energy. This is the Hamiltonian operator will act on the wave function and is equal to the energy and the wave function, where me is the mass of the electron and psi of r is the total wave function of the electron. In order to solve this Schrödinger equation, the Cartesian coordinates are converted to spherical polar coordinates r, theta, phi, which are defined as follows. So if x, y, z, the coordinates in Cartesian coordinates, and r, theta, phi spherical polar coordinate system, and if we draw this coordinate system r, theta, phi, then it will look like this. If you point here, whose distance is r, and the point is P, r, theta, phi, and also x, y, z. Then we draw a perpendicular on the xy plane. Just see, this is m, then this is x, this is y, and this is z. This angle is theta, and this is r, and this angle is phi. And the relation between the Cartesian coordinate system and the spherical polar coordinate system is this. So if you know the spherical polar coordinates are theta phi, then we can calculate the um, coordinates in the Cartesian coordinate system x, y, z, and inversely and conversely, if we know x, y, z, then we can find r theta phi by squaring. So here, if we square this x, y, z and add, then we'll see that x square plus y square plus z square equal to r square. So is r equal to the square root of x square plus y square plus z square. And if we divide, from this relation, theta is equal to cos inverse z divided by r, and r is this. And if we divide this equation by this, then we'll have tan phi equal to y by x. So phi equal to tan inverse y by x. So you see from these three equations that if we know the Cartesian coordinate system of a point x, y, z, we can immediately calculate the coordinates in the spherical polar coordinate systems are theta phi, where for the whole space r ranges from 0 to infinity, and theta ranges from 0 to pi, and phi ranges from 0 to twice pi, and x ranges from minus infinity to plus infinity, y is also minus infinity to plus infinity, and z is also from minus infinity to plus infinity for the whole space. Okay. Now the Schrodinger equation, this equation we are now going to convert to spherical polar coordinate system, because the hydrogen like atom is spherically symmetric, particularly in the s orbital it is spherically symmetric. So it's easy to solve this equation if we convert this equation into a spherical polar coordinate system. We know del square in spherical polar coordinate system is this. Therefore, the Schrödinger equation becomes then this is the Schrödinger equation in arc theta phi coordinate system. This equation can be simplified to this. Okay, we shall apply separation of variable techniques to solve this equation. Technique by assuming that the total wave function is a function of r theta phi, and which is the product of three wave functions. One is capital R, which depends on small r, and then capital theta, which depends on theta, and capital phi, which depends on phi. Okay, so this psi, if this psi is substituted here in this Schrödinger equation, and after multiplying by r square sin square theta divided by r theta phi, the Schrödinger equation then becomes and Okay, now we multiply both sides of the above equation by this. We get now we observe in the left hand side that the um, third term of this equation, this is the third term, and this term depends only on the variable phi, and this phi does not appear in any other terms. So this third term must be third term must be a constant. Let this constant be minus m square. This is a constant. Then we can then write down 1 by phi minus. So if we rewrite this, then this one can be written as okay. Let us say this is equation number 1. This is the equation for phi. And if we put this this term as minus m square here, then this equation. Okay, let us clean the board first. And we get sin square theta divided by r del by del r square del r by del r theta by theta and the third term, which is minus m squared. Okay, dividing the above equation by sine square theta, uh, then we get 1 by r del by del r square this, and we rearrange the terms. Which is equal to m square by sine square theta minus by theta into sine theta. Now in this equation also we see that the left hand side depends only on the small r variable and the right hand side depends on theta, so both sides must be a constant. Left hand side of this equation depends only on r, and the right hand side depends only on theta. Therefore both sides must be equal to a constant. Let this constant be L into L plus 1, where L is an integer. The two separated equations then become one by theta one by sine theta del theta let's say this is equation number 1, and the radial equation will be This is equation number 3. Thus we have 3 ordinary differential equations. Equation 1 for the variable small phi, equation 2 which is the equation for theta, and the equation 3 which is the equation for r. Equation 1 has straightforward solution. And the solution is this. Where a is a constant, normalization constant, the boundary conditions in this case is that the wave function, the capital phi of phi must be single valued. This must be single valued. Since phi of phi is equal to phi of phi plus twice pi. So if we use this, then we have this, which gives us and this is satisfied if m equal to 0, plus minus 1, plus minus 2, plus minus 3, and so on. And the normalization constant also normalization constant a can be obtained by normalizing phi. So is limits of small phi 0 to twice pi, so is this it must be equal to 1, which will give us this. Therefore the capital phi is equal to 1 by square root of twice pi, then e to the power I m phi. So this is the solution for the azimuthal angle phi. The solutions of the other 2 equations, the equations for r and theta, these equation 2 and 3, they have solutions. These solutions are complicated. The mathematical calculations show that the solutions of those 2 equations are these. I'm now going to write down those solutions. And the solutions for the theta equation is this. And the equation, the radial wave function has solution this. This is n nl, and this is e to the power minus rho by 2 and rho to the power L and capital L n plus L, here twice L plus 1, and is a function of rho, where rho is equal to twice Z divided by n a naught and R, where this constant a naught, what is the constant? This solution the function PLM is known as the associated Legendre polynomials. And the solution, capital R, which is obtained by this function L n plus L twice L plus 1, this is known as the associated Legendre polynomials. We would like to stop here. In the next lecture, we shall continue the discussion about the quantum theory of hydrogen-like atom. We shall also discuss about the concept of atomic orbitals and the total solution of the hydrogen-like atom.